Hello, and welcome to another exciting episode of Algorithm Analysis and Design. I'm your host and your professor, Dr. John Baugh. For this lecture, we're going to be discussing another algorithmic technique called backtracking. So, what is backtracking? Well, it's a problem-solving strategy. It can be viewed as systematic trial and error. We're going to explore the solution space incrementally, and if a partial solution cannot lead to a valid solution, we abandon it, and that's called backtracking. You go back. It works like depth-first search on a state space tree. Real-world analogies, or situations where you could use it. Maze navigation, so walk until you reach a dead end, and then you would backtrack to the last, that should be fork, I believe. Last fork. There we go. And try another path. So Sudoku or crosswords, for example, fill in numbers. See, missing another N. Or words. Erase when contradictions appear. So you basically are removing characters, possibly, if you're in a crossword or a Sudoku, and you have to work your way back. Scheduling or puzzles, so you can try different options, undo those options when they don't fit. Key characteristics of backtracking. They are recursive. They have depth-first search-like exploration, as mentioned. They build solutions one step at a time. We backtrack when a constraint is violated or there's no further progress possible. These are also suitable for constraint satisfaction problems, or CSPs, which are pretty extensively used in many different areas, but in particular areas of artificial intelligence. Typical output would be a feasible solution, and the one thing to keep in mind with backtracking is that these are not always optimal. They're just a feasible solution. They're useful when the solution space is large. Constraints allow pruning, meaning we remove entire swaths of possible solutions because they aren't really possible solutions. And optimality is less important than feasibility. Common applications, we'll talk about the n-queens problem, for example, and Hamiltonian circuits in particular. They can be applied to Sudoku and puzzles, as mentioned, also subset generation and combinatorial search. So let's look at it in the algorithmic paradigm landscape. So algorithmic paradigms recap, just to remember where we are. Divide and conquer. We started with divide and conquer earlier on. We break the problem into independent subproblems and then combine the results. Dynamic programming, we found out that if we have overlapping subproblems, we can reuse the solutions as well with memoization and tabulation. So if you have overlapping subproblems, you can apply dynamic programming techniques, and we're typically reusing the solutions, and what it's saying is that we're actually taking advantage of things that have been calculated already. Okay. So greedy algorithms, we look for the locally optimal choice, and no backtracking is used in those types of algorithms. And now that we're at backtracking, we can think of it again as systematic trial and error, undo bad choices, and that should be prune, not prunce. I'm not sure what that means. Okay, so prune impossible paths. All right. Okay, so backtracking versus brute force. So if we look at backtracking, we try to distinguish it from brute force. Brute force enumerates all possibilities and then checks feasibility at the end. So you take this huge collection full of all these possible paths or solutions, and then you check feasibility at the very end. Backtracking, you prune early when a partial solution is infeasible, and you don't take that one any further. Saves enormous amount of time when constraints eliminate many candidates, okay, early on. For the n-queens problem, brute force would generate all n to the n placements of the queens, okay, and the idea with if you've played chess, when you put a queen on the board, it can attack other pieces vertically, horizontally, meaning rows, columns, and also on diagonals. The n-queens problem is you take a board, an n by n board, and you place queens on it. You place n queens. For example, if it's a standard 8 by 8 chessboard, you would place 8 queens on it, And a solution would be, how do we place those 8 queens without any of them being able to attack any of the others? And it sounds very complicated, but there are solutions, and backtracking gives us a good way to solve those types of problems. But you can have as small as the 4 queens problem and still have a solution. Backtracking tells us to stop as soon as 2 queens threaten each other instead of going down that path. Brute force would say we go down that path and every other path, every possibility. What about backtracking instead of versus brute force? Let's look at backtracking versus dynamic programming, which we have looked at. So with dynamic programming, we have an optimization focus. We reuse solutions of subproblems, and by doing that, we avoid recomputation. With backtracking, we are focused not on optimization, but feasibility. Is it a possible solution? That's the question we're asking. It abandons infeasible branches early. We don't generate them. Now, although we visualize it as a tree, you're not always really, generating an actual tree data structure, but the state space tree does refer to the different paths we go down. And with backtracking, we can actually come back if we start going down or notice that a path will not yield any success. Okay, use cases. So for dynamic programming, the use cases are typically things like shortest path, the knapsack's optimal value, specifically 0-1 knapsack. Backtracking, we solve things like Sudoku, Hamiltonian paths, feasible layouts. We'll talk about other applications as well. What about backtracking versus greedy algorithms, which we spoke about fairly recently? With greedy, we have irrevocable choices, meaning you cannot revoke the choice or backtrack, basically, is what it's saying. Once you make that choice, that's your choice. It's fast, but it may miss solution or optimal solutions. With backtracking, the choices can be undone. It guarantees feasibility if a solution exists. Okay? So it guarantees it'll find a solution. It does not necessarily mean it'll find the optimal solution. As an analogy, with greedy algorithms, we always pick the shortest line at the store, never switching. Backtracking is try a line. If it's blocked, go back and try another. Backtracking is kind of between brute force, which is, doing complete enumeration, and dynamic programming greedy type styles, which are looking for an optimal solution to certain problems. It's best when constraints allow heavy pruning, meaning if you can reduce the search space, a lot of the search space with various pruning techniques, then that is when it performs the best. We're learning this because it'll provide another paradigm that we'll talk about later on called branch and bound, which adds bounding functions for optimization. So we start with kind of a backtracking technique and add optimization to it. So what's the general strategy? Where does backtracking fit in? So it represents the solution as a sequence of choices. Okay, so we keep track of the choices. Each partial solution is a node in a state space tree. The root could represent an empty solution. Children would be extensions by one more decision. And then when they have children, that's one more decision. But you can always go back. That's kind of the idea. When you get to a leaf, though, you have a complete solution. Now, that solution may or may not be valid, okay? But you could get to the leaf. So step-by-step growth. Build the solution incrementally, as mentioned, at level K. So if you picture a tree, you've got level 0 at the root, level 1, level 2, or some people start with 1, then go to 2, from root being level 1, but level 0 often is the case. At a given arbitrary level, but specific level K, first K elements are fixed, okay? You extend by picking from the candidate set SK plus 1, okay, that's what's left. If that set is not the empty set, meaning there are still things we can look at, this right there would, if it's an empty set, it would lead to a dead end, so we would backtrack. Otherwise, we continue the recursion. Okay, so if it leads to an infeasible or empty solution, we backtrack. Some search tree visualization here. We see that each branch, every time we branch off here, the C1, C2, C3 are just choices. You can assume that they also have subtrees potentially. Those are the choices. Now we're focusing in on, say, choice 1. Let's say choice 1 has further choices, okay, another level of choices, say 1.1, 1.2, 1.3. If a branch fails, we cut off that node and its subtree. For example, if I'm in C1 and I go down this path right here to this node with the X on it, I wouldn't know it had an X until I check it out. When I check down here and I notice it's infeasible, and it's not going to lead to a feasible solution, I can basically disregard that node, and then this one may be the parent of an entire subtree. And that subtree may be very, very large. We don't know. But it is possible to do that, and we might just say, hey, that's not feasible, so we're just going to go back, and we disregard the rest of this tree. We don't even go any further. Brute force would just keep on chugging until you do the full depth first search of the whole search space. C1 could also check the middle, find a reasonable path to pick, and then go down there. And then go over here, sees that that's not feasible, so it cuts that off. Same thing you would do with C2, C3, etc. So backtracking can be looked at like it's depth first search with pruning added. Okay, with pruning. Some key steps in backtracking. If you're looking at kind of a very high-level algorithmic view of what we do with backtracking in general, we start with an empty partial solution, choose the next candidate to extend our solution, and then you do a feasibility check. You ask, is the constraint satisfied? If it is, then we recurse, meaning you keep going. Otherwise, if it's not feasible, then we prune that entire subtree, which could be a single node or it could be thousands of nodes. We don't know. And then we backtrack. If the complete solution is found, then we output it, but we continue search until all candidates are explored. Recursive note. So backtracking is inherently recursive. Each recursive call extends the solution by one step. And again, I think I've explained it in videos before, but I use spaced repetition when I teach. So I will be repeating myself and exploring it in different ways, different contexts, so you remember different things about it more commonly. So you will see some stuff you're like, didn't we go over that? The answer is usually yes, we probably did at some point. Okay, so each recursive call, again, we extend solution by one step. Base case, the solution is complete, valid, or invalid. Recursive case, loop over candidates, recurse, and undo as necessary. Example of a generic search. So input would be something like a set of choices, for example, board positions for, say, our queen, vertices in a graph problem, items in some sort of list or scheduling situation. We output one or more valid configurations. The algorithm will explore feasible partials. We would keep those. And then infeasible partials, we prune those. Guarantees are that every feasible solution will be found. Okay, and no solution is generated twice. Those are the two guarantees. Now, again, by feasible, we are not saying optimal. Okay, that's a whole other step. Okay, that is not in the purview of backtracking. Promising and pruning. So a promising node is a partial solution that could still lead to a valid solution. So in our state space, we look at a specific node if it is a partial solution and there is it's not a full solution yet, but it could lead to a full solution later on. There's still hope. Then we call that a promising node. Examples would be something like in n queens problem, placing queens so far with no conflicts. We haven't placed all the queens yet, but there's no conflicts yet. So we consider that promising. We continue exploring from promising nodes. On the contrary, we don't explore down paths with non-promising nodes. That's where the pruning comes in. So a non-promising node is a partial solution that cannot lead to a valid solution. For example, in the n queens problem, if two queens threaten each other, okay, say they're in same diagonal or same column, part of the initial conditions of this problem is that we put them in separate rows, but the additional constraints would be that if they're in the same column or diagonal, then that is not promising because we've already, basically said that you have two queens threatening each other. There's no way to complete it that way, so why do we keep going? You don't keep placing additional queens down that route. You just stop and then go back. So the action would be prune the subtree and backtrack immediately. Okay? So how do we do, or what does this pruning look like? Backtracking is, again, depth first search with pruning. So you go as deep as possible in the tree, but with pruning. For each node, if it's promising, we expand its children. If it's non-promising, we prune the entire subtree. That saves exponential time by cutting off branches early. Okay. A promising function is an application-dependent test. Okay, it's not going to be the same function when you're doing n-queens versus a graph problem or something different, Hamiltonian circuit or something like that. So it is domain or application specific, and it will decide if the node is worth exploring. So an example with n-queens would be check if the new queen conflicts with previous queens. If not, then it's promising. Hamiltonian circuit would be something like check if a path repeats a vertex already visited. Okay, and we're not at the end yet. Okay, so if it's a circuit, it will come back to the initial node, but it shouldn't do that too early. If you visit the same vertex that you came from too early, or any vertex that isn't the beginning vertex, then you have a problem and it's not promising. So the goal for the promising function itself, this is one component of this, just like you have things like in dynamic programming, you have something that calculates the pivot for quicksort or something like that. We have this specific subroutine here, this promising function gets special attention because it's very important. It should be cheap enough to compute, but it should be strong enough to prune early. Okay, so if it's super strong, but it's not cheap to compute, you might be wasting more calculations calling this promising function than you would gain by pruning, and that's not a good situation. We don't want to be in that. So the efficiency trade-off is that if we do good at pruning, that equals big savings. But evaluating the promising function also takes time, so we have to keep that in mind. If the check's too simple, leads to little pruning and wasted search. If the check is too complex, pruning cost outweighs the benefit. Here's some classic examples. I've alluded to the n-queens problem before, so we want to make sure that we know what that is. So the problem statement is we place n queens on an n by n chessboard. This one's kind of colorful. It's a little hard to see what's going on. But let me just do that real quick so you can see what's going on. Each of these is a square. You can kind of see that it looks like it's on graph paper, but each of these, where these colorful lines intersect, those are squares on this 8 by 8 board. Okay, now there's a queen right there. Okay, so the constraint... and it's also n queens on an n by n chessboard. So this is the 8 queens problem. It's an 8 by 8 chessboard. Then that's, the 8 queens problem. So if it was the 9 queens problem or the 13 queens problem, they would be on 13 by 13 or 9 by 9 or what have you. The constraint is that no 2 queens can attack each other. In other words, they cannot be in the diagonal. Okay, these black lines here are indicating the attack patterns that are available from the queen. So if you're in the same row as the queen, then that's not feasible. You can't do that because the queen can attack you. If you're in the same column, then we also have an infeasible scenario. And also if you're in the diagonal, okay, that's bad too, because the queen can attack along rows, columns, and diagonals. The goal would be to find all possible placements, or at least one, that would solve this. So the naive approach, kind of a brute forcey type approach, would be try every arrangement of n queens on n squared squares. The total possibilities would be n squared factorial over the quantity n squared minus n factorial. For n equals 8, this is astronomically large. Okay, it's around 4.4 times 10 to the 13 possibilities. Clearly, that's infeasible. Okay, it's intractable. We need pruning. So the smarter setup observation is that we only need 1 queen per row. Okay, just seeing that means you don't have to check any of the other squares in the same row as the queen that you're in. So that eliminates, for the first row, if it's the 8 queens problem, that eliminates, once you place a queen in that row, that eliminates 7 other cells just in that row that you don't need to check out. Okay, so that reduces the problem space from n squared factorial to n to the n possibilities. It's still huge, but it's more manageable now with further pruning. Further refinement would be 1 queen per row and column, and that leaves only n factorial permutations to consider. Oh joy. Okay. Build solutions row by row. At row K, try placing a queen in each column. Promising function would be no two queens in the same column, no two queens in the same diagonal. So you build in promise by only putting a queen in each for a given row in a specific column. So since you're going and looping through the different rows, you're preventing them any queens from being in the same row because you're literally using that as kind of a loop iteration variable. Okay. So once you have that, then you have to make sure that the queens are not in the same column or same diagonal. If it's promising, you recurse to the next row. If it's not promising, you backtrack. All right, so what about the 4 queens problem? So if we reduce this a little bit, you've got the root is the empty board. Each level of row decisions, branches are column choices, and non-promising placements pruned early. Since it's a whole lot of art, and I am not an artist, I decided to just link to this the Geeks for Geeks page on this. This is a reasonable discussion of it, and it also has the artwork, so it's nice, with a whole lot of ads. So the 4 queens problem, again, is placing 4 queens on a 4x4 chessboard so that no queens attack each other. Okay, we know how they attack. All right, so we place each queen one by one in different rows, starting with the topmost row. While placing a queen in a row, you check for clashes with already placed queens. For any column, there is no clash. For any column, if there is no clash, then mark that row and column as part of the solution. In case, if no safe cell found due to clashes, then backtrack. In other words, that is, undo the placement of the recent queen and return false. So here's the initialized board. It's empty, okay, just like the root of our state space tree. Put our first queen, Q1, in cell 00. So I have that right there, and we can see that the X's are just indicating where does that queen attack, okay? So put the next queen. Now, this is kind of skipping a step. We would check this. We would say if that queen's there, queen 1, then we would check it. Okay, can't be in the same column, so that's not good. And now if we put it in 1-1, that's on the same diagonal, so that also doesn't work. So we can put them, or try to put it there. There's Q2. Now they don't conflict, okay? So we're good so far. At row 2, there's no cell at which we are safe to place the Q3, okay? Because if I put it for row 2, I try to put it there, it's being conflicted by this queen. If I put it there at 2-1, this queen can get it. Same with 2-2, same with 2-3. So we have a problem. All right, so we have to backtrack and remove queen 2 because there's really no arrangement that makes this work. There's still a safe cell in row 1, so we put, instead of having Q2 in row 1, or I'm sorry, in column 2, we put her in column 3. Okay, so Q1 and Q2 are still not clashing, so we can try that one. Next, put the queen, Q3, if we tried at 2-0, then that clashes with Q1, but if we go to 2-1, that puts Q3 right at the 2-1, their Q1 cannot attack it, and neither can Q2. So that is actually a promising node. So there's unfortunately though, if you keep going, in row 3, there's nowhere to put the queen. So if I put a queen there, it clashes, there it clashes, there it clashes, there it clashes. Okay, so nothing works. We have to backtrack and remove queen 3. Again, there's no safe cell in row 2, so we backtrack again and remove queen 2 from row 1, because we assume with Q2, the reason we got to this placement was because we tried each of these cells. We tried 1-0, we tried 1-1, we tried 1-2, and we ended up at 1-3. There's nowhere else to go in that row that makes it safe. So now you have to backtrack one more level and go back up to where the Q1 is and move her. Okay, so now we place Q1 at cell 01. Place her there. Okay. Now let's try Q2. Well, Q2 cannot go at 1, 0, 1, 1, or 1, 2 because Q1 can attack it. So we'll try Q3. Good, it's safe. Place Q3. Or cell 3. Cell 1, 3 is what I meant. Now, for this one, If I place queen 3 at 2, 0, that's actually safe already. I don't have to go any further for this round. So it's still promising because there's no queen in its rows or columns. If you place q4 and move to the next row, okay, if I go to q4, I can't go here, can't go there, but I can go here. q4 can be placed at 3, 2. So I have q1 here at 0, 1, q2 at 1, 3, q3 at 2, 0, and q4 at 3, 2. This is one of the arrangements that all the queens are safe. So it is considered one of the solutions. All right. They do give you some C++ and Java, Python, C# JavaScript solutions as well. Okay, pretty good. Here's some pseudocode. This is some pseudocode kind of based very similarly on what they had on Geeks for Geeks. It's a little high level here. So it doesn't put in a lot of the details, but if the row greater than n, print the board, means we found a solution. Otherwise, for each of the columns, check if it's promising. If it is promising, place the queen, call n queens recursively, and then call remove queen if you need to backtrack. Okay. The promising function looks like this. For previous equals 1 to row minus 1. For things in the same column, if they're in the same column, you return false. If it gets past the column test, this is how you test the diagonal conflict. So you say if the absolute queen of previous minus call, okay, the queen at previous minus call is equal to row minus previous. That's kind of a little trick there. You could put it explicitly if you needed to, but this is one trick that would solve the problem. So to give you an idea of solutions and growth for this problem, for n equals 4, there are 2 solutions. It's the only solutions. Okay, we saw one of them, and then the mirror image would be another. For n equals 8, okay, there are actually 92 solutions, so there's quite a few. For large n, this grows rapidly, but still solvable with pruning. Next up, we have the Hamiltonian circuit, or cycle. So a Hamiltonian circuit, also called a Hamiltonian cycle or tour, is a path in a graph that visits each vertex exactly once. So no more queens right now. We're on to a different problem. Hamiltonian circle is a path in a graph that visits each vertex exactly once. So that's a Hamiltonian path in general. But when it returns back to the starting vertex, that's what makes it a circuit or a cycle. Not all graphs even have a Hamiltonian circuit. It's heavily related to the traveling salesperson problem. So why would brute force fail? Well, to find a Hamiltonian circuit, with brute force, we would generate all permutations of vertices, which is n factorial. That's just the permutations. Then you check each adjacency and return edge. So for even a relatively small graph for n equals 10, 10 factorial is 3,638,800 possibilities. Backtracking avoids exploring paths that revisit a vertex too soon. The backtracking approach is we start at a root vertex and extend the path one vertex at a time. The promising function is the next vertex is adjacent to the last vertex in the path. The vertex hasn't already been visited. If the path is non-promising, we prune it immediately. If the path included all vertices and an edge back to the start, we find a solution. So finding a Hamiltonian circuit. So given this graph here, this is a K4 graph, so it's a complete graph with 4 nodes. Every vertex is connected to every other vertex, right? So we start at A. Okay, from A, you can branch to B, C, or D. Then from B, let's say I choose B, the next valid moves would be C or D. We don't go back to A because that would create a cycle. We're returning too early. Okay, we haven't included the other nodes yet. We continue until you either reach a path that revisits a vertex. We would prune that. So if I go from A to B to D and then D back to B, that would be bad. We don't want that. So we would prune that node in the state space tree, not in the actual graph, but in the, remember that hypothetical kind of state space tree of all the different solutions. That's what we prune. We reach a couple cycle a complete cycle covering all the vertices. That would be the other continue condition until we reach a complete cycle covering all the vertices, and that would mean that we found a Hamiltonian circuit. So if we keep going and we didn't have one that revisited a vertex except after we've gotten all the nodes included and back to the original one, then we keep going unless that's the case. So state space tree, this is just the tree looking at all the different possibilities. So at each level is the next vertex in the path. Remember, each level is the next choice. So from A, if I choose B, my next choices include C or D. I can't choose A, so I don't have A down here as another choice. So we can do C or D, and then from C, you can only pick D, and then D, it's kind of implied here, but you would go back to A. Okay, this is for the path leading up to the end that would bring you back to the cycle in this case, just to make it a little easier to visualize. If you're at node A at the beginning and you pick C, then the only other options are B and D. Okay, and then past that, the B, you can only go to D, and the D, you can only go to B. For D, you can go to B or C, can't go back to A. And if you're at B, you can't go to D, you can't go to A because it's too early. So you can only go to C. And then if you picked C, you would go to B. Here's some pseudocode for the Hamiltonian. Pass in the path and n if the length of the path is equal to n, and the edge of the path at n to path 1, we print out the path and start. So we found a Hamiltonian circuit, if that's the case. Otherwise, so that's basically kind of a base case there, right? Otherwise, for the vertices and the neighbors of the last path, if the vertex is not in the path, okay, basically it's not calling a separate function, it's doing a promise check though. So if the vertex is not in the path yet, we call Hamiltonian of the path plus v comma n. So this is the recurse. So we add that new vertex to the path and then tell it total number and then recurse. So it's again this one's used in the traveling salesperson problem with weights, network routing, and circuit design and scheduling. NP complete, there's no known polynomial time solution. That would be a game changer if someone came up with a polynomial time solution. In fact, if you came up with a polynomial time solution, you would also win you would solve the P equals NP problem as well. Because all you need to do is solve one of the NP complete problems and you would get that glory. Because everything is reducible or polynomial time reducible in NP complete to any other problem in NP, which includes all the other NP complete problems. So anything that's considered the hardest of the NP problems, if you solve one of them, that means that you have solved all of them. Now, some computer scientists think that such solutions do exist. I'd say the majority believe they do not, meaning there's no known polynomial time solution that we don't believe there are, but no one has proven it one way or the other. Okay, I'm in the pessimist crowd. I don't believe that there is a polynomial time solution for the traveling salesman problem, the Hamiltonian path, or anything else like that. Optimal problems, of course, or solutions. Backtracking works for small, medium graphs, sets the stage for things like branch and bound. So better pruning with cost bounds when we get to that. So what does general backtracking and pseudocode or template look like for this type of solution? Well, backtracking is recursive, depth first search with pruning. Remember, recursive, depth first search with pruning. That's backtracking. So again, the core idea is we build a partial solution. If it's complete, then we report that solution. Otherwise, we extend the solution one step at a time. If the extension is promising, we recurse. If it's non-promising, we backtrack or undo what we just did. Here's general pseudocode. If partial solution is a complete solution, we output it, print it. Otherwise, for each candidate, if it's promising, then we add C to the partial solution and then call recursively backtrack. You can see that this is doing the depth first search here. So we add C to our partial solution, and then you don't, go back in the for loop and go for the next one. You actually recursively call backtrack. So you're going deeper in the tree before you go wider. Okay, so it's not breadth first search, it's depth first search. The promising function, So problem-dependent check for feasibility returns true if the partial solution can lead to a valid full solution. Examples again, n queens and a Hamiltonian. Did we? I think that's a repeat of a earlier slide, but I think that was intentional. So Hamiltonian next vertex is adjacent plus not visited yet. Keynotes on the implementation, the backtracking problems or backtracking solutions are always recursive, okay, just like depth first search. The undo step or backtrack is essential to restore state. We can find one solution and just stop at the first success. That's one option. That's more efficient. If we just want one solution, then that's great. We just need one, great. Or we can find all solutions. That means we have to enumerate fully all of the solutions. That is also possible. It is generally more complex. You need more time, more resources to do that. Works well with global variables or arrays to track partial states. For example, queen positions or visited vertices. For backtrack in C++, this is just the C++ code kind of matching the earlier code in the pseudocode. And then here's the Python skeleton right here. Okay, you would have to define things like is complete and promising and stuff like that. All right. Alrighty. Let's look at the complexity. So baseline complexity, again, always recursive, just like DFS, undo step. Let me see here. That's a goof. That should not be on there. Sorry, that slide does not belong. That's in a different set. So why is it still useful? Complexity consideration. So pruning eliminates vast portions of the tree. Many real instances are solved. Works best when the constraints are strong, and bad branches can be recognized early. The queen's problem, the state space size with n equals 8. We saw earlier that there's a whole lot going on, obviously. So it's 4.4 times 10 to the 13 possible placements for brute force. But with pruning, instead of that many possible placements, we would have 15,720 nodes visited on average with pruning. Okay. So it shows how an exponentially large state space can be reduced dramatically to something more manageable in practice. Okay. Factors affecting the efficiency. So time per node, cost to generate next candidate, strength of promising function, how much pruning occurs. Okay, so is it super complex promising function or super simple? And that has an impact on how successful it is. So the overhead of the checks, falling under that, we have balance, the pruning power plus check time, of course, and then problem structure, sparse versus dense graphs, and the number of constraints. Upper bound analysis. So theoretically, worst case is the size of the full tree. For the n queens problem, it's a factorial problem, which is not so good. For Hamiltonian, also not so good in factorial. But in practical terms, often far fewer nodes visited if we have the backtracking technique applied. Difficult to analyze the savings formally, but it's best understood through empirical results, which we saw earlier with the 4.4 times 10 to the 13 versus 15,000. All right, important takeaways are that backtracking has exponential worst case, often tractable in practice. Success depends on good problem foundation. Strong constraints lead to effective pruning. Okay. It also gives us a bridge to the branch and bound, which we will talk about later on. All right, applications beyond chess and graphs. We might want to look at some of the other things that it is used for. Constraint satisfaction problems, or CSPs. Many real-world problems involve choosing values that satisfy some constraints. Backtracking is a natural fit. Examples would be our Sudoku issue, the crossword or word fill puzzles, and scheduling tasks with time or resource constraints. Combinatorial search and optimization, the subset sum knapsack or knapsack problems. We've got decision versions of those. We can generate subsets, prune when overweight or infeasible, and partitioning problems, dividing elements into valid groups. These are backtracking is also useful when useful when approximate or heuristic solutions aren't applicable. AI in game solving, so problems like the 15 puzzle or Rubik's cubes, we can do partial searches on those, the search space. And game tree exploration, so minimax search using backtracking with pruning. There's alpha beta pruning and other forms as well. Robotics or path planning in constrained environments are also another thing that we can do. Further real-world applications, circuit design, wiring without overlaps, network routing, the path feasibility checks are important. Software verification, so checking all valid execution paths against the constraints, and in bioinformatics, where we apply computer science to biological problems or biochemical problems. So sequence alignment and motif search under constraints. So bioinformatics is a very, very important area in healthcare. It becomes more and more important. We would say that things like drug discovery is heavily related to it. So we can find new pharmaceuticals to fight, fight new illnesses and things like that. But when you're dealing with specific sequences, sequence alignments are very important in bioinformatics as well. If it weren't for bioinformatics, the pandemic would probably still be going on. So it's kind of the unsung hero of, coming up with the treatments and vaccines and sequencing of the virus so it could be understood better. All right, so summary. Backtracking is a systematic way to explore solution spaces. It's a depth-first style search. Undoing choices, that's the pruning, when the constraints fail. Okay, so I'll get that in your head if it hasn't already stuck there from the multiple times I've said it, that backtracking is basically depth-first search with pruning. Depth-first search with pruning. And the pruning is undoing the choices. So promising and pruning, cut off infeasible branches early, works well for constraint satisfaction problems, classic problems like N-queen, Hamiltonian, and beyond that, Sudoku, scheduling, routing, and verification. The complexity is that it's exponential in the worst case, but pruning often makes it practical. Notice it says often. It does not mean we'll get an optimal solution, but it makes it more feasible. Bridges us to the branch and bound, which we will talk about in a later lecture. So backtracking plus bounding function for optimization. All right, that's what I've got for you this lecture. I'll talk to you later. Bye-bye.